Moving right along, let's go further with this and look at the net energy. So we had done it differently before. So now here we are looking at the annual mean meridional sections of incoming solar radiation, absorbed solar radiation, and emitted long wave radiation, and the resulting net radiation. Okay, so this is again, you can think of it as the zonal mean meridional. You can see irradiance or watts per meter squared. So the absorbed solar, as we saw before, high at low latitudes. The albedo has been taken care of. Remember, we did this before of a pi r squared times 1 minus alpha, where alpha is the albedo, which we said is an average of 0.3 for the Earth. So that is what this is. So obviously this is 342 minus about 30% already done. And the emitted long wave is this curve here. So there is actually a little dip in the deep tropics, which we already mentioned when we looked at convection and said deep convective clouds make the cloud tops pretty cold. So deep tropics on average is emitting at a colder temperature than the regions of the tropics, for example, where the outgoing long wave is actually higher. Remember sigma t to the fourth, right? So t is cooler in the deep tropics compared to off tropics. Obviously, as you go to higher latitudes, temperatures are continuously getting colder, and there is again this asymmetry of the southern hemisphere versus the northern hemisphere, considering the land and the ocean, Antarctica, Arctic, etc. Right? So the difference of these two is obviously the net radiation that the Earth absorbs. So there is the net radiation. You have probably already been exposed to this before. You have net energy gain over these latitude ranges where the difference is greater than 0. And there is a net energy loss. There is a net energy deficit beyond a certain latitudes towards the poles, with our asymmetry showing up again. Okay, so what does that mean? If there is a net energy gain in some latitudes, then it should get warmer and warmer and warmer. And if there is a net energy loss, then they should get colder and colder. Obviously, this doesn't happen. Even though there is a contrast, poles are colder than the deep tropics. They don't keep warming and cooling respectively. So what does that mean? That means there are processes that are constantly moving energy from the latitudes of net energy gain to the latitudes of net energy loss. Obviously, that's what gives us the weather and climate, as I've said already several times. Once you have the atmosphere in motion, that's going to drag the ocean as well. And we'll see that ocean also has another mode of circulation driven by density differences as opposed to just being dragged by the winds. So you can look at these curves and basically figure out how much energy has to be moved towards the poles in each hemisphere. Okay, very simple. Excess energy has to be moved into these regions of deficit energy. So transport of energy is implied, and here is a calculation. Northward energy transport deduced by top of the atmosphere measurements of incoming and outgoing solar radiations. So incoming and outgoing solar and terrestrial radiations from Irby satellites. So there is a satellite that was flying above the atmosphere and could measure both shortwave flux and long-wave flux. And the units here are in petawatts. Okay, this is northward flux, which means the coordinate y is positive in the northward direction. So negative numbers here just mean that the heat transport is from the lower latitudes towards the pole. Here it's positive towards the North Pole. Here it's negative because it's in the opposite direction, but it's towards the South Pole. So we're moving energy from the area of excess energy that's in here towards the poles here. So that's about 6 petawatt in both hemisphere. So there is essentially energy divergence from the latitudes which are receiving excess energy. Petawatt is 10 to the 15 watt, which is a common unit when you have energies at these large numbers. This obviously gives us the meridional structure. So this is how you typically do the zonal mean. Zonal mean of any particular variable x bar over latitude and depth, so latitude and height. So latitude and height is given by, because it's a sphere, 1 over 2 pi, 0 to 2 pi. X lambda is the longitude at particular latitude and at a particular height in the atmosphere. So you integrate over all longitudes, 0 to 2 pi. Okay, dateline to dateline, let's say, or Greenwich meridian to Greenwich meridian. So let's look at the average temperature. We have seen this once before. Temperature, as we said, is not a conservative quantity, and it is obviously got these values that are warm in the low latitudes and near the surface. As you go towards higher latitudes, temperatures cool off because poles are colder. Higher latitudes are colder than lower latitudes. As you go into the atmosphere from the surface, we have already seen that the troposphere has continuous cooling towards the tropopause, and then there is a warming towards into the stratosphere, right? So you can see you start with an average of about 25 degrees centigrade, drop off by about 600 hectopascal here, and above 200 you are hitting the tropopause. So you can see this sharp gradient here, and you can see that the temperatures are dropping off continuously down to minus 75 degrees centigrade, and then they begin to increase again, go from minus 75 to 70, 60, minus 65, minus 60, and so on, where the stratosphere starts. So we are not showing the stratosphere here. So we will see later on that there are lots of cute things here, right? If there is cold air and heavier air here, and there's warm, lighter air here, why doesn't the air just rush in towards the tropics and push the warm water, warm air up above it? Right? If you have a tank, let's say, and you put cold water in the middle and warm waters at the edges, obviously warm water is lighter and it's going to flow in, and push cold water is heavier, so it's going to come in and push the warmer, lighter water up, right? That doesn't happen. Why? You can guess. Basically because we are not in a tank that's just sitting there. It is a rotating planet, which means we are beginning to say that the rotational effects are going to have a strong impact on maintaining gradients in the horizontal and in the vertical as well. Simple enough, but this is a beginning of trying to imagine those impacts. So this is a stratified fluid. It's nicely split into layers. So there are scales that we will look at. What determines the scale that separates this positive temperature to negative temperature, right? So there is a balance between the stratification and rotation, and we'll derive a scale that depends on some particular parameters of the atmospheric temperature and so on. Okay, so there is a lab experiment we'll look at which shows how that works. So we'll also look at the potential temperatures and so on to make this concept clearer, because we said temperature is not conservative, but potential temperature is conservative for dry processes, and moist potential temperature is conservative for moist and dry processes, right? Remember the definitions.